quenching of star formation in galaxies, the process by which they cease making new stars, can occur through various mechanisms, both internal and environmental. Mass quenching tends to affect the most massive galaxies, possibly through feedback from active galactic nuclei that heat or expel gas, while environmental quenching removes gas from galaxies in dense clusters through RAM pressure stripping and other processes. Understanding which mechanisms dominate in different mass ranges and environments remains a key goal in galaxy evolution studies. Kinematic misalignments between different components of galaxies, such as gas rotating in a different plane than the stars, often indicate past mergers or accretion events. The Cartwheel galaxy provides an extreme example where a collision completely reorganized the gas distribution while leaving the stellar component less affected. These misalignments gradually decay over time as dynamical friction and other processes bring the components back into alignment. The specific star formation rate, defined as the star formation rate per unit stellar mass, provides a normalized measure of how vigorously a galaxy is forming stars relative to its existing stellar population. Actively star-forming galaxies define a main sequence in the plot of star formation rate versus stellar mass, with a nearly linear relationship indicating that more massive galaxies form stars faster in absolute terms. sometimes exceeding 10 to 1. These systems may form in environments with low merger rates that allow disks to grow undisturbed over billions of years. Or they might have unusual dark matter halos that stabilize thin disks against gravitational instabilities. Their fragile structures make them useful laboratories for studying disk dynamics and stability. The Kenny-Kutschmidt law relates the rate of star formation per unit area in galaxies to the gas surface density, typically finding that star formation rate scales with gas density to a power of about 1.5. This relationship holds across wide ranges of scales and environments, from individual molecular clouds to entire galaxies, suggesting that the physical processes governing star formation operate similarly everywhere. Deviations from the relation can indicate unusual conditions or the influence of additional factors beyond simple gas density. Lyman alpha emitters, galaxies detected through their strong emission of Lyman alpha light from hydrogen, provide samples of young star-forming galaxies at high redshifts. The Lyman alpha photons produced by massive stars ionizing their surroundings must escape through the galaxy's neutral hydrogen without being absorbed, a process that depends on the distribution of gas and dust. Studying these galaxies helps astronomers understand star formation and gas properties in the early universe. Active galactic nucleus feedback can occur in two modes: a radiative mode where radiation pressure from the accreting black hole drives winds, and a kinetic or jet mode where mechanical energy from jets and bubbles heats the surrounding gas. Observations suggest that the radiative mode dominates at higher accretion rates, while the kinetic mode operates when black holes accrete slowly. Both modes can quench star formation and regulate galaxy growth, helping to explain why the most massive galaxies are red and dead despite residing in deep potential wells. Galactic bars serve as highways that transport gas from the outer disk toward the central regions where it can fuel star formation and black hole growth. The gravitational torques exerted by the bar remove angular momentum from the gas, causing it to spiral inward along the bar until it reaches the central kiloparsec. This process can build up nuclear starbursts and pseudobursts over hundreds of millions of years, demonstrating how internal dynamical processes can drive galaxy evolution even in the absence of mergers. The Tully-Fisher relation shows less scatter than would be expected from the range of star formation histories among spiral galaxies, suggesting that disks settle into configurations where their rotation curves, luminosities, and masses are tightly linked. This regularity may reflect fundamental constraints from angular momentum conservation during galaxy formation or self-regulation through feedback that maintains galaxies near a characteristic state. Outliers from the relation often show signs of recent interactions or unusual gas contents. Clumpy galaxies at high redshift display irregular morphologies, with multiple bright clumps of star formation distributed across their disks rather than concentrated in spiral arms. These massive clumps may form through gravitational instabilities in gas-rich disks and could migrate inward over time to build up galactic bulges. The prevalence of clumpy morphologies at high redshift reflects the higher gas fractions and more violent disk dynamics in the younger universe. Cosmic New, the epoch around 10 billion years ago when the universe was about a quarter of its current age, represents the peak era of galaxy assembly and star formation. During this time, galaxies formed stars most vigorously, black holes grew most rapidly, and the cosmic web began to take its current form. Studying galaxies at Cosmic New provides crucial insights into the processes that created the galaxy populations we observe in the present-day universe. Environmental preprocessing describes the transformation of galaxies in groups stellar mass to halo mass ratio peaks at halo masses around 10 to the 12 solar masses, corresponding to galaxies similar to the Milky Way, suggesting that these systems convert baryons into stars most efficiently. At lower masses, supernova feedback ejects gas before it can form stars, while at higher masses, active galactic nucleus feedback prevents gas from cooling. This peak efficiency leaves an imprint on the galaxy stellar mass function and helps explain the observed demographics of galaxies. Tadpole galaxies display distinctive one-sided tails of stars and gas, drawn out by tidal interactions with passing companions. The head of the tadpole contains the main body of the galaxy with ongoing star formation, while the tail stretches behind it, marking the path through space. Over time, these tails may disperse or fall back into the main galaxy, but they serve as visible tracers of past close encounters and the ongoing process of galaxy interactions shaping galactic structure. The mass-metallicity relation shows that more massive galaxies contain higher abundances of heavy elements in their stars and gas, reflecting their deeper potential wells that retain supernova ejecta, while less massive systems lose metals to galactic winds. This relation evolves with redshift, with galaxies at earlier times showing lower metallicities at fixed mass, consistent with them having experienced fewer generations of star formation and chemical enrichment. The scatter in the relation correlates with star formation rate, with more actively star-forming galaxies showing lower metallicities, possibly due to dilution from infalling pristine gas. Compact massive galaxies at high redshift, much smaller than massive galaxies today while containing similar stellar masses, present puzzles for galaxy evolution models. These dense nuggets may represent the cores of modern elliptical galaxies before they grew extended envelopes through minor mergers, or they might evolve through expansion driven by stellar mass loss in dynamical processes. Understanding how these compact systems connect to present-day galaxies requires careful modeling of both their formation and subsequent evolution. The radial migration of stars within galactic disks, driven by resonances with spiral arms and bars, can move stars significant distances from their birth radii while preserving their circular orbits. This process mixes stellar populations and can explain why stars with similar ages show a range of metallicities, and why the metallicity gradient in disks appears shallower than predicted by simple chemical evolution models. Radial migration demonstrates that galaxy disks are not static structures, but dynamically evolving systems, even in the absence of major perturbations. Jellyfish galaxies in clusters display spectacular trails of gas and young stars, stripped from the main body of the galaxy by ram pressure as it plunges through the hot intracluster medium. These tails contain ongoing star formation, where the stripped gas has been compressed, creating streams of bright blue stars following the galaxy's orbital path. Studying jellyfish galaxies provides unique insights into the stripping process and demonstrates that star formation can occur even in gas being removed from galaxies. The assembly bias effect shows that dark matter halos with the same mass but different assembly histories can cluster differently in space, with implications for how galaxies populate halos and evolve in different environments. Halos that formed earlier tend to be more clustered, potentially because they reside in denser regions that collapsed earlier. This effect complicates efforts to connect galaxy properties to halo masses and must be accounted for in models of galaxy formation and evolution. Bulbless disk galaxies, pure disk systems without significant central concentration, challenge simple pictures of galaxy formation that predict all disks should develop bulges through instabilities or mergers. These systems may have avoided major mergers throughout their histories and resisted Schechter function provides a mathematical description of the galaxy luminosity and stellar mass functions, characterized by a faint end slope, a characteristic luminosity or mass, and an exponential cutoff at high luminosities. This functional form fits observations reasonably well across cosmic time, though the parameters evolve as galaxies grow and the brightest systems become more common. Deviations from the Schechter form at the faint end remain uncertain due to observational difficulties in detecting the faintest galaxies. Molecular gas in galaxies, primarily molecular hydrogen traced through observations of carbon monoxide emission, serves as the immediate reservoir for star formation. The conversion efficiency from molecular gas to stars, quantified by the depletion time, varies between galaxies and environments, with starbursts depleting their molecular gas much faster than normal spirals. Understanding what regulates this conversion efficiency remains crucial for predicting future star formation in galaxies and explaining their diverse properties. Counter-rotating stellar components in some galaxies, where different populations orbit in opposite directions, provide evidence for accretion of gas or stars from external sources with angular momentum misaligned with the main galaxy. These configurations can remain stable for billions of years and affect the dynamics in star formation in the galaxy. The presence of counter-rotation constrains formation scenarios and indicates complex merger histories. The universal rotation curve of spiral galaxies shows a characteristic shape that rises steeply in the inner regions and flattens in the outer disk, with the shape determined by the combination of baryonic and dark matter distributions. This universality suggests that similar physical processes shape all spiral galaxies, though individual systems show variations that correlate with total mass and other properties. The flat rotation curves extending to large radii provide strong evidence for dark matter halos. Galactic archaeology in external galaxies attempts to reconstruct their formation histories by analyzing the spatial distributions, kinematics, and chemical compositions of their stellar populations. Resolved stellar observations of nearby galaxies reveal complex structures including stellar halos, streams, and shells that trace past accretion events. While integrated light spectroscopy of more distant systems probes average properties, these studies show that most large galaxies have experienced numerous mergers and interactions throughout their lives. The submillimeter galaxy population, detected through their intense emission at submillimeter wavelengths from dust heated by vigorous star formation or active galactic nuclei, represents some of the most luminous objects in the universe. These dusty starbursts, particularly common at redshifts around 2, form stars at rates reaching thousands of solar masses per year, often in compact regions that will likely evolve into massive elliptical galaxies. Their discovery revealed a population of intense star formation, hidden from optical surveys by dust obscuration. Morphological quenching describes the observation that galaxies with higher central stellar concentrations tend to have lower specific star formation rates, even after accounting for stellar mass and environment. This correlation might reflect the role of bulges in stabilizing gas against gravitational collapse, or could indicate that the processes building bulges also quench star formation. Disentangling cause and effect in this relationship remains challenging. The cosmic web filaments connecting galaxy clusters contain warm-hot intergalactic medium at temperatures of 100,000 to 10 million degrees, a phase predicted to contain a large fraction of the universe's baryons. This material has proven difficult to detect directly, but shows up as absorption features in the spectra of distant quasars and through stacking analyses of many systems. Understanding the properties of filaments helps complete the census of baryonic matter suggesting additional physical connections, perhaps related to the history of their dark matter halos. Explaining conformity requires understanding the interplay between environment, halo assembly history, and galaxy properties. Warps in galactic disks, where the outer disk bends away from the main plane, appear in many spiral galaxies, including the Milky Way. These features may result from gravitational interactions with satellites, misalignment between the disk and dark matter halo, or accretion of gas with misaligned angular momentum. Warps can persist for billions of years and affect the dynamics and evolution of the outer disk where they occur. The fundamental metallicity relation connects galaxy stellar mass, gas phase metallicity, and star formation rate, with galaxies at fixed mass showing lower metallicities when forming stars more rapidly. This anti-correlation likely reflects dilution of enriched gas by inflows of metal-poor gas from the cosmic web, which simultaneously fuel star formation and reduce average metallicity. The relation provides insights into how gas flows regulate both star formation and chemical evolution. Brightest cluster galaxy alignments with the large-scale structure demonstrate connections between galaxy formation and the cosmic web, with the major axes of these massive ellipticals often pointing toward neighboring clusters and filaments. This alignment may reflect the anisotropic accretion of matter along filaments during the assembly of clusters and their central galaxies. Such alignments offer tests of structure formation theories and the role of the cosmic web in shaping galaxies. Disk truncations in spiral galaxies, where the exponential surface brightness profile cuts off sharply at some radius, may represent the maximum extent to which gas has settled into the disk, or where the surface density drops below the threshold for star formation. The truncation radius correlates with galaxy properties and can change over time as galaxies accrete gas or lose it through stripping. Some galaxies show extended faint disks beyond the main truncation, possibly formed from accreted material. The quenching timescale, how long it takes galaxies to cease star formation after some triggering event, varies between galaxies and quenching mechanisms. Environmental quenching through RAM pressure stripping can remove gas and halt star formation within a few 100 million years, while quenching through gas starvation takes several billion years as galaxies exhaust their existing supplies. Observations of post-starburst galaxies and galaxies in transition provide constraints on these timescales. Ionized gas kinematics in galaxies, measured through emission line spectroscopy, reveal rotation curves, velocity dispersions, and outflows that trace the dynamical state of the gas. Comparing gas and stellar kinematics shows whether the two components are in equilibrium or whether the gas has been disturbed by accretion or interactions. Kinematic disturbances correlate with enhanced star formation, supporting the idea that mergers in gas accretion trigger starbursts. The halo occupation distribution describes the probability that a dark matter halo of a given mass hosts a certain number of galaxies, providing a statistical connection between galaxies and dark matter structure. This framework helps interpret galaxy clustering measurements and constrain galaxy formation models. The central galaxy in a halo typically has a mass that increases with halo mass, while satellite galaxies appear in higher mass halos, with numbers increasing for more massive systems. Galaxy size evolution shows that at fixed stellar mass, galaxies at high redshift tend to be more compact than their local counterparts, suggesting that galaxies grow in size as well as mass over cosmic time. This size growth may occur through minor mergers that deposit stars in the outer regions, adiabatic expansion driven by mass loss from evolved stars, or other physical processes. Understanding size evolution connects to questions about how compact massive galaxies at high redshift evolve into the specific angular momentum of galaxies, their total angular momentum per unit mass, connects to their morphology and formation history. Disk galaxies retain most of the angular momentum acquired during their formation, while elliptical galaxies contain less specific angular momentum, possibly lost during dissipational mergers that formed them. The relationship between stellar mass and specific angular momentum, often called the fall relation, provides constraints on models of how galaxies acquire and retain angular momentum. Edge-on spiral galaxies reveal the vertical structure of galactic disks, showing thin disks of young stars and gas overlaid by thicker distributions of older stars. Dust lanes cutting across these galaxies trace the distribution of interstellar material in the disk plane. Measuring scale heights at different radii and for different stellar populations provides insights into disk formation, dynamical heating, and the role of merger history in shaping disk structure. AGN obscuration, where dust surrounding active galactic nuclei blocks direct views of the central engine, creates diverse observational appearances depending on viewing angle and the distribution of obscuring material. Unified models propose that the same type of active galactic nucleus can appear as different observed types depending on orientation, with torus-shaped distributions of dust blocking our view from certain angles. Infrared and X-ray observations can penetrate the dust and reveal hidden active nuclei. The Lyman break technique identifies high redshift galaxies by their characteristic spectral break caused by neutral hydrogen in the intergalactic medium, absorbing photons blueward of the Lyman alpha. Transition. This technique has enabled surveys of galaxies at redshifts greater than 3, when the universe was less than 2 billion years old, revealing populations of young star-forming galaxies that help reionize the universe. The dropout technique uses similar principles to find even higher redshift galaxies. Wandering black holes, supermassive black holes displaced from galaxy centers by gravitational recoil during mergers, or by three-body interactions in merging systems, may exist in the outskirts of galaxies, or even between galaxies. These objects remain difficult to detect unless actively accreting, but simulations predict they should be common in galaxies that have experienced multiple mergers. Finding wandering black holes would provide important tests of merger dynamics and gravitational wave recoil scenarios. The silk damping scale represents the size below, which primordial density fluctuations were erased by diffusion in the early universe, setting a minimum mass for the first dark matter halos and potentially the first galaxies. Structures smaller than this scale had to form through fragmentation of larger systems rather than direct collapse from primordial fluctuations. This scale leaves an imprint on the properties of the smallest galaxies and may explain features of the galaxy mass function at low masses. Intergroup light in galaxy groups, analogous to intracluster light but in lower mass systems, consists of stars stripped from group members through tidal interactions. The fraction of total light in this diffuse component increases with group mass and dynamical age, serving as a record of past interactions. Measuring intergroup light helps constrain the merger histories of groups and test model of how galaxy interactions redistribute stellar mass. Damped Lyman alpha systems, identified as strong absorption features in the spectra of background quasars, represent neutral hydrogen gas in protogalactic disks and galaxy halos. These systems contain the majority of neutral hydrogen in the universe at high redshifts and serve as the raw material for star formation in young galaxies. Studying their properties, metallicities, and evolution provides insights into the gas reservoirs of galaxies during the peak epoch of star formation. Galaxy downsizing refers to the phenomenon where the most massive galaxies formed their stars earliest and ceased star formation first, while lower mass galaxies continue forming stars to later times. This observational pattern seems counterintuitive, since more massive systems should take longer to assemble, but it reflects the more effective quenching mechanisms operating in massive galaxies through active galactic nucleus feedback. Downsizing shapes the observed relationship between galaxy mass, color, and star formation properties. The Sunyaev-Zeldovich effect, where cosmic microwave background photons gain energy while passing through hot gas in galaxy clusters, provides a way to detect clusters independent of redshift and to measure the properties of the intracluster medium. This effect creates a characteristic decrement and increment in the cosmic microwave background spectrum that can be used to find clusters and constrain cosmological parameters. Combined with X-ray observations, Sunyaev-Zeldovich measurements help determine cluster masses and test hydrostatic equilibrium. Cooling flows in galaxy clusters were once thought to allow gas to cool rapidly and accrete onto the central galaxy at high rates. But observations show that cooling proceeds much more slowly than predicted. Active galactic nucleus feedback likely heats the gas and prevents runaway cooling, creating a self-regulating system where cooling and heating balance. The details of this feedback mechanism and how energy is distributed through the cluster remain active research areas. Polar bulges, kinematically distinct components in some disk galaxies with orbital planes perpendicular to the main disk, may form from accreted satellites or through bar-driven gas inflow. These structures provide additional evidence that galaxies are built up through multiple processes and that their components can have diverse origins and kinematics. The stability of polar bulges constrains the shape of galactic gravitational potentials. Merger trees trace the assembly histories of galaxies backward through cosmic time, showing how they grew through mergers and accretion of smaller systems. These trees, constructed from cosmological simulations or inferred from observations, reveal the hierarchical nature of structure formation and help connect the properties of galaxies today to their formation conditions. Different galaxies with similar present-day masses can have vastly different merger histories, leading to diverse structural and kinematic properties. The escape fraction of ionizing radiation from galaxies, the fraction of ultraviolet photons capable of ionizing hydrogen that escape into the intergalactic medium, plays a crucial role in the reionization of the universe. Measuring this fraction remains challenging because local galaxies typically have low escape fractions due to dust absorption and neutral gas, while high redshift galaxies that reionize the universe are difficult to observe directly. Connecting measurements at different redshifts helps constrain when and how reionization occurred. Feedback-regulated star formation models propose that galaxies self-regulate their star formation through the energy and momentum injected by supernovae and stellar winds, creating a balance between gas consumption through star formation and gas ejection through feedback. This regulation helps explain why galaxies convert only a small fraction of their gas into stars and maintains the characteristic exponential disk profiles observed in spirals. Fine-tuning the strength and implementation of feedback remains a key challenge in galaxy formation simulations. Ancient globular clusters orbiting galaxies serve as archaeological relics of the early stages of galaxy formation, their ages indicating when the first intense bursts of star formation occurred. The metallicities, spatial distributions, and kinematics of globular cluster systems preserve information about the merger history and early evolution of their host galaxies. Multiple populations of globular clusters with different properties often indicate that galaxies assembled through mergers of smaller systems that each contributed their own cluster populations. The stellar mass assembly history of galaxies can be reconstructed through stellar population synthesis models that connect observed colors and spectra to the ages and metallicities of stellar populations. These studies reveal that massive elliptical galaxies assembled most of their stellar mass early in cosmic history through intense bursts of star formation, while lower mass spirals have more extended star formation histories continuing to the present day. Environmental effects modify these histories, with cluster galaxies typically showing earlier quenching than field galaxies of similar mass. Dual active galactic nuclei in merging galaxies provide glimpses of supermassive black hole pairs before they coalesce, offering opportunities to study black hole growth during mergers and test predictions of binary evolution. Finding these systems requires identifying two distinct active nuclei or distinguishing them from single offset nuclei, a challenging observational task. The frequency of dual active galactic nuclei constrains models of black hole feeding during mergers and the timescales for binary formation. The dark matter distribution in galaxies, inferred from rotation curves, stellar dynamics, and gravitational lensing, typically shows approximately spherical halos extending far beyond the visible matter. The density profiles of these halos, particularly whether they have flat cores or steep cusps near the center, provide tests of dark matter models and galaxy formation physics. Baryonic processes like gas cooling, star formation, and feedback can modify the dark matter distribution through gravitational interactions. Simulations of galaxy formation have progressed from following only dark matter to including increasingly sophisticated treatments of gas physics, star formation, and feedback processes. Modern simulations can reproduce many observed properties of galaxy populations, including their masses, colors, sizes, and morphologies, though challenges remain in matching all observables simultaneously. The success of these simulations validates our broad understanding of galaxy formation, while highlighting areas where our physical models need refinement. The environmental dependence of galaxy properties extends beyond simple correlations with local density to include effects of halo mass, distance from cluster centers, time since infall, and assembly history. Galaxies in rich clusters differ systematically from those in poor groups and isolated galaxies, with the differences reflecting the varying strengths of environmental processes. Disentangling the effects of different environmental factors requires large samples spanning diverse environments and careful statistical analyses. Lie-alpha blobs, enormous clouds of Lie-alpha emitting gas extending hundreds of thousands of light years around some high redshift galaxies, may represent gas being accreted onto forming galaxies, material expelled by galactic winds, or light from central sources scattered by surrounding gas. These mysterious objects mark sites of intense activity in the early universe and may trace the formation of massive galaxies and galaxy clusters. Understanding their power sources and relationship to galaxy formation remains an active research area. High-velocity clouds in the Milky Way's halo, clouds of neutral hydrogen moving at velocities inconsistent with simple disk rotation, may represent gas accreting onto our galaxy from the intergalactic medium or material expelled by galactic fountains falling back. These clouds contain mostly primordial composition gas, supporting the accretion interpretation for at least some systems. Their accretion rate may help sustain star formation in the Milky Way's disk. The baryon cycle in galaxies describes the continuous flow of gas into galaxies from the cosmic web, conversion into stars, ejection by feedback processes, and eventual return to fuel future star formation. This cycle operates over billions of years and involves complex interactions between cosmological gas accretion, star formation, stellar evolution, and feedback. Understanding each stage of the cycle and how they connect remains essential for explaining galaxy evolution. Extended star formation, entitled TAILS, demonstrates that star formation can occur in gas clouds removed from galaxies during interactions, creating associations of young stars and star clusters in intergalactic space. Some of these tidal dwarf galaxies may survive as independent systems, while others will fall back into the parent galaxies or disperse. The existence of star formation in tails shows that the right conditions exist even in highly disturbed gas. The galaxy correlation function quantifies how galaxies cluster in space, showing that galaxies are not randomly distributed, but preferentially found near other galaxies. This clustering reflects the underlying dark matter distribution and its growth through gravitational instability. Measurements of galaxy clustering at different scales and redshifts constrain cosmological models and test theories of how galaxies populate dark matter halos. Metallicity gradients in galaxy disks, with higher metallicities near the center declining outward, reflect inside-out growth where central regions formed stars earlier and enriched more rapidly. The slope of this gradient depends on the balance between star formation, radial gas flows, and mixing processes. Interactions and mergers can flatten gradients by redistributing gas, while continued star formation steepens them. So, observed gradients encode information about a galaxy's history. The gene's mass, the minimum mass required for a gas cloud to collapse under its own gravity against thermal pressure, sets the characteristic mass scale for star formation within galaxies. This mass depends on gas temperature and density, explaining why star formation occurs primarily in cold, dense molecular clouds. Feedback processes that heat gas increase the gene's mass and suppress star formation, regulating the overall star formation rate. Satellite galaxies of the Milky Way and Andromeda, including systems like the Large Magellanic Cloud and M32, provide unique laboratories for studying galaxy evolution in detail, impossible for more distant systems. These satellites span a range of masses, morphologies, and star formation histories, offering insights into dwarf galaxy evolution, tidal interactions, and the effects of the host galaxy environment. Their proximity allows detailed stellar population studies and measurements of individual stars. The cosmic star formation rate density, the average rate of star formation per unit volume in the universe, peaks at redshift around 2 when the universe was approximately 3 billion years old, then declines steadily to the present. This evolution reflects changing gas supplies, feedback efficiency, and merger rates over cosmic time. Integrating the star formation history gives the buildup of stellar mass in the universe and can be compared to the observed stellar mass density to check consistency. Bulgeless galaxies, also called pure disk galaxies, challenge formation scenarios predicting that all disks should develop bulges through secular evolution or mergers. These systems may represent recently formed galaxies that haven't had time to develop bulges, or they might inhabit low-density environments with few interactions. Their existence demonstrates that multiple evolutionary pathways lead to the diversity of observed galaxy types. The age-metallicity relation in galaxy disks connects the average metallicity of stars to their age, generally showing that younger stars have higher metallicities, reflecting ongoing chemical enrichment. Scatter in this relation reveals the stochastic nature of star formation and mixing, while systematic deviations can indicate gas inflows or outflows. The relation differs between galaxies and environments, encoding their diverse chemical evolution histories. Galaxy groups and clusters continue growing through the accretion of smaller groups and individual galaxies, a process ongoing in the present-day universe. Galaxies falling into clusters experience RAM pressure stripping, tidal interactions, and other environmental effects that transform their properties. Observations of infalling groups and galaxies at various stages of this process help constrain the timescales and mechanisms of environmental transformation. The stellar-to-halo mass relation peaks at a specific halo mass, where galaxies convert baryons into stars most efficiently, with lower efficiency both above and below this peak. This non-monotonic relation reflects the varying effectiveness of feedback processes at different mass scales, with supernova feedback dominating at low masses and active galactic nucleus feedback at high masses. The peak shifts slightly with redshift as the balance between gas accretion and feedback evolves. Central molecular zones in galaxies, the innermost few hundred parsecs where gas densities and kinetic temperatures reach extreme values, host unique star formation conditions quite different from the outer disk. Star formation in these regions may proceed less efficiently despite high gas densities, possibly due to turbulence, tidal forces, or magnetic fields. Understanding star formation in central molecular zones helps explain the properties of galactic nuclei and nuclear star clusters. The merger fraction of galaxies, the fraction experiencing significant mergers at any given time, decreases from high redshift to the present as the universe expands and galaxies become more separated. Major mergers were common when the universe was younger and denser, contributing significantly to galaxy growth and transformation. The declining merger rate helps explain why massive elliptical galaxies formed their stars early, while lower mass systems continue forming stars today. Photoionization by the cosmic ultraviolet background maintains the ionization state of diffuse gas in galaxy halos and the intergalactic medium, affecting how this gas cools and accretes onto galaxies. The intensity of this background builds up as more galaxies form and emit ionizing radiation, creating a feedback loop where star formation in galaxies affects the gas supply for all galaxies. Variations in the ultraviolet background with cosmic time influence the evolution of galaxies and the intergalactic medium. Spiral density waves in galactic disks, rotating patterns of enhanced density that create the visible spiral arms, move at different speeds than the stars and gas, allowing material to enter and leave arms while the pattern persists. Gas clouds entering an arm get compressed, triggering star formation that illuminates the arm with bright blue stars. The pattern can be maintained by gravitational interactions with satellites, bars, or self-gravity of the disk, depending on the galaxy. Color gradients in elliptical galaxies, with redder colors in the center and bluer outskirts, reflect gradients in age, metallicity, or both. These gradients may result from inside-out formation, where central regions assembled first, or from subsequent accretion of lower metallicity material in the outskirts. Detailed stellar population analyses can separate the contributions of age and metallicity to color gradients, constraining formation scenarios. The virial theorem relates the kinetic and potential energies of gravitationally bound systems in equilibrium, allowing mass estimates from observable quantities like velocity dispersions and sizes. Applied to galaxies and galaxy clusters, this theorem provides a fundamental method for measuring total masses, including dark matter. Deviations from virial equilibrium indicate ongoing assembly or recent perturbations. Transitional post-starburst galaxies, showing features of both star-forming and quenched galaxies, may represent systems caught during the brief period when star formation shuts down. These rare objects provide crucial constraints on quenching timescales and mechanisms, showing how quickly galaxies can transform. Their properties depend on the quenching mechanism, with merger-driven quenching producing different observational signatures than environmental quenching. Dark matter substructure within galaxy halos, the remnants of smaller halos that merged but didn't completely dissolve, affects the dynamics of stars and satellites and may be detectable through gravitational lensing. The abundance and survival of subhalos tests dark matter models and provides insights into how hierarchical assembly builds galaxy halos. Comparing simulated subhalo populations to observed satellite galaxies helps constrain galaxy formation physics. Starbursting dwarf galaxies, small systems experiencing intense star formation far above their normal rates, may be triggered by gas accretion or interactions with larger galaxies. These bursts can significantly alter dwarf galaxy properties, enriching them with metals, driving winds that remove gas, and creating extended stellar halos. The short duty cycle of starbursts in dwarfs makes it challenging to catch many in the act, but their effects on galaxy evolution can last for billions of years. The rotation measure of polarized radio emission through galaxy halos traces magnetic field strengths and gas densities, revealing that galaxies possess large-scale, ordered magnetic fields extending into their halos. These fields may be amplified from weak seed fields through dynamo action driven by turbulence and differential rotation. Magnetic fields affect gas dynamics, cosmic ray propagation, and possibly even galaxy formation itself, though their full role remains under investigation. Galactic chimneys and worms, channels through which hot gas from stellar feedback can escape the galactic disk into the halo, may play important roles in driving galactic winds and enriching the circumgalactic medium with metals. These structures form where multiple supernovae create overlapping bubbles that break through the disk, allowing pressurized hot gas to vent into the lower density halo. The efficiency of this venting affects how much energy and mass feedback can inject into the halo versus being contained within the disk. Smooth stellar halos surrounding galaxies contain stars on highly eccentric orbits quite different from the ordered rotation of disk stars, suggesting these stars formed in satellite galaxies, later disrupted and accreted. Chemical tagging of halo stars can sometimes identify groups that originated in the same progenitor satellite, even billions of years after the disruption event. The mass and structure of stellar halos encode the accretion history of galaxies over cosmic time. Wet and dry mergers describe galaxy collisions, where the participating galaxies contain significant gas reservoirs versus those between gas-poor systems. Wet mergers between gas-rich galaxies trigger starbursts and can form compact remnants, while dry mergers between passive ellipticals simply add their stellar masses together without star formation. The prevalence of wet versus dry mergers evolves with cosmic time as galaxies exhaust their gas supplies and the universe expands. The extended disk phenomenon, where some galaxies show star formation and stellar populations extending well beyond the traditional optical radius, challenges simple models of disk formation that predict sharp truncations. These extended disks may form from late accretion of gas with high angular momentum, or they might reflect inside-out growth continuing to larger radii than previously thought. Their discovery has revised upward estimates of total disk masses and sizes. Pristine dwarf galaxies that have formed few or no stars throughout cosmic history may exist in large numbers, but remain essentially invisible in current surveys. These dark galaxies would consist almost entirely of dark matter and primordial gas, having failed to form stars due to feedback from reionization, low halo masses, or environmental effects. Finding such objects would provide important tests of galaxy formation theories and dark matter models. The missing baryons problem notes that direct observations account for only about half the baryonic matter expected from Big Bang nucleosynthesis and cosmic microwave background measurements. Much of the missing baryons likely reside in the warm-hot intergalactic medium at temperatures of 100,000 to 10 million Kelvin. Too cool to emit X-rays efficiently, but too hot to produce strong absorption lines. This material traces the large-scale structure of the cosmic web and represents baryons that never collapsed into galaxies. Supermassive black hole masses correlate tightly with properties of their host galaxy bulges, including bulge mass, luminosity, and stellar velocity dispersion, suggesting a fundamental connection between black hole growth and galaxy evolution. This correlation implies that feedback from active galactic nuclei and galaxy formation processes are intimately linked, with black holes and bulges growing together through cosmic time. Understanding the physical origin of these correlations remains a major goal in galaxy evolution studies. Resonances in disk galaxies, locations where the orbital frequencies of stars match the rotation rate of spiral patterns or bars, create gaps and rings as stars avoid or pile up at resonant radii. The locations of these resonances depend on the pattern speed and can be identified through observations of stellar kinematics and gas distributions. Resonances affect the transport of angular momentum and gas through disks, influencing their evolution over gig-year timescales like islands in an infinite ocean, each one a collection of billions upon billions of stars bound together by gravity's gentle embrace. Our own Milky Way galaxy stretches across about 100,000 light years, a spiral of stars, and does it slowly rotating through space over the course of hundreds of millions of years. When you look up at the night sky, almost every point of light you see belongs to our own galaxy, though a few fuzzy patches reveal distant galaxies millions of light years away. The Andromeda Galaxy, our nearest large galactic neighbor, floats approximately 2.5 million light years from Earth, yet it appears as a soft smudge visible to the naked eye on dark, clear nights. This massive spiral galaxy contains roughly 1 trillion stars, making it somewhat larger than our Milky Way. And the two galaxies are gradually drifting toward each other at about 70 miles per second. In about 4 billion years, these two cosmic giants will begin a slow, graceful merger that will take millions of years to complete, eventually forming a single elliptical galaxy. Galaxies come in several beautiful forms, each with its own character and story. Spiral galaxies like our Milky Way feature elegant arms that wind outward from a central bulge, these arms glowing with young blue stars and pink nebulae where new stars are being born. Elliptical galaxies appear as smooth, rounded collections of stars with little dust or gas, their stellar populations generally older and redder. Having dwarf galaxies, though individually containing only millions to billions of stars rather than hundreds of billions, outnumber their larger cousins and may hold important clues about how galaxies form and evolve. The largest structures in the universe are galaxy superclusters, vast collections of galaxy clusters and groups extending across hundreds of millions of light years. Our local group belongs to the Laniakea supercluster, a structure containing about 100,000 galaxies and stretching 500 million light years across. These superclusters aren't randomly arranged, but form a cosmic web of filaments and walls surrounding vast empty voids, creating a structure that resembles foam or a sponge when viewed on the largest scales. Stars within galaxies orbit the galactic center in complex patterns, determined by the distribution of mass throughout the galaxy. Our sun takes about 230 million years to complete one orbit around the Milky Way center, a period sometimes called a galactic year. During Earth's history, our solar system has completed only about 20 orbits, meaning the last time we occupied our current position in the galaxy. Dinosaurs had not yet evolved, and life on Earth consisted primarily of simple marine organisms. The rotation of galaxies reveals something mysterious about the universe. When astronomers measure how fast stars orbit in galaxies, they find that stars far from the galactic center move much faster than they should based on the visible matter present. This discrepancy suggests that galaxies contain far more mass than we can see, a mysterious substance called dark matter that interacts through gravity, but doesn't emit, absorb, or reflect light. Dark matter appears to form vast halos around galaxies, extending far beyond the visible disk and containing several times more mass than all the stars and gas combined. Looking back in time by observing distant galaxies, astronomers have discovered that galaxies in the early universe looked quite different from modern ones. Many early galaxies were smaller, more irregular, and underwent more frequent mergers as they grew through cosmic time. The universe began as a nearly smooth sea of matter with only tiny density fluctuations, and over billions of years, gravity amplified these fluctuations, pulling matter together to form the first stars and galaxies when the cosmos was only a few hundred million years old. The beautiful colors we see in galaxy images often represent different types of stellar populations and ongoing star formation. Young, hot blue stars indicate regions of active star birth, typically found in spiral arms in irregular galaxies where gas and dust remain abundant. Older, cooler red stars dominate elliptical galaxies and the central bulges of spirals, representing stellar populations that formed billions of years ago. Pink and red regions often mark nebulae, where hydrogen gas glows as it's excited by radiation from newly formed stars. Some of the most spectacular galaxies visible from Earth include the Sombrero Galaxy, named for its resemblance to the broad-brimmed Mexican hat, with its bright central bulge and distinctive dark dust lane. The Whirlpool Galaxy showcases clearly defined spiral arms and appears to be interacting with a smaller companion galaxy, their gravitational dance triggering bursts of star formation. The Cartwheel Galaxy displays a striking ring structure created by a collision with a smaller galaxy that passed through its center like a stone dropped into a pond, sending waves of star formation rippling outward. Galaxies experience collisions and mergers throughout cosmic time, though these events unfold over millions of years rather than occurring as catastrophic crashes. When galaxies collide, their stars almost never actually hit each other because the distances between stars are so vast compared to their sizes. Instead, the galaxies pass through each other like ghosts, their gravitational fields interacting and distorting their shapes, while shock waves compress gas clouds and trigger intense bursts of new clusters are loose collections of young stars born from the same molecular cloud, slowly drifting apart over tens or hundreds of millions of years as they orbit the galaxy. Globular clusters are dense, spherical collections of hundreds of thousands to millions of ancient stars, orbiting the galaxy in an elongated path that take them far above and below the galactic disk. These globular clusters represent some of the oldest objects in the universe, their stars having formed more than 12 billion years ago. The space between galaxies, called intergalactic space, is even more empty than interstellar space within galaxies. In galaxy clusters, this space contains extremely hot, diffuse gas that emits X-rays and contains more mass than all the visible stars in the cluster's galaxies. This gas represents material that never fell into galaxies during their formation, instead remaining in the gravitational well of the cluster as a whole. The temperature of this gas, often tens of millions of degrees, reflects the enormous energy of motion possessed by galaxies as they orbit within the cluster. Galaxies grow through a combination of internal star formation and mergers with other galaxies. Smaller galaxies falling into larger ones add their stars to the growing system, while gas flowing into galaxies from the cosmic web provides fresh material for new generations of stars. The history of a galaxy can be read in its stellar populations, with the chemical composition, age, and distribution of stars providing clues about past mergers, periods of intense star formation, and interactions with the intergalactic environment. The Hubble Space Telescope's deep field images, created by pointing the telescope at seemingly empty patches of sky for days at a time, reveal thousands of galaxies at various distances and stages of evolution. These images show that wherever we look in the universe, we find galaxies, each one a collection of billions of stars with potentially trillions of planets. The sheer number of galaxies in the observable universe, estimated at several hundred billion, reminds us of the vast scale of creation and our small but special place within it. Some galaxies emit powerful radio waves from their cores, visible to radio telescopes as vast lobes extending far beyond the optical galaxy. These radio galaxies host supermassive black holes that launch jets of high-energy particles at nearly the speed of light. These jets extending for millions of light years and creating enormous bubbles of radio emission in the intergalactic medium. The energy required to power these jets comes from matter falling into the black hole, with a portion of the gravitational energy being converted into kinetic energy of the outflowing particles. Within our own galaxy, the Orion Nebula serves as one of the closest regions of active star formation, located about 1,300 light-years from Earth. This stellar nursery contains hundreds of young stars less than a few million years old, still surrounded by the gas and dust from which they form. Observations of regions like this help astronomers understand how stars and planetary systems form within galaxies, providing insights into the processes that created our own sun and planets 4.5 billion years ago. The Milky Way's spiral structure consists of several major arms, including the Perseus arm, the Sagittarius arm, and the Scutum Centaurus arm. With our solar system located in a smaller feature called the Orion Spur between the Perseus and Sagittarius arms. These spiral arms aren't fixed structures made of particular stars, but rather density waves that move through the galactic disk. Regions where stars and gas pile up temporarily before moving on in their orbits. As gas clouds enter a spiral arm, they get compressed, triggering star formation that lights up the arm with brilliant blue stars and pink nebulae. Dwarf spheroidal galaxies represent the most common type of galaxy in the universe, though their faintness makes them difficult to detect. These small, faint galaxies contain a few million to a few billion stars spread across a volume several thousand light years across. makes them nearly invisible against the night sky. Many dwarf spheroidals orbit larger galaxies as satellites, and they appear to contain high fractions of dark matter relative to their visible matter, making them excellent laboratories for studying this mysterious substance. The processes that regulate star formation in galaxies remain an active area of research. Galaxies can't simply convert all their gas into stars as quickly as possible because various feedback mechanisms regulate the process. When massive stars explode as supernovae, they inject energy into the surrounding gas, heating it and potentially driving it out of the galaxy entirely. Active galactic nuclei can also heat or expel gas, preventing it from cooling and forming stars. These feedback processes help explain why galaxies convert only a small fraction of their gas into stars over cosmic time. Starburst galaxies experience periods of exceptionally intense star formation, creating new stars at rates hundreds of times faster than in normal galaxies. These bursts often result from galaxy collisions or mergers that funnel large amounts of gas into the central regions of galaxies, compressing it and triggering the rapid formation of massive stars. The intense ultraviolet radiation from these young stars can heat the surrounding gas and dust, causing the galaxy to glow brightly in infrared light, sometimes making it one of the most luminous objects in the universe at infrared wavelengths. The concept of galactic habitable zones suggests that certain regions of galaxies may be more favorable for the development of life than others. Too close to the galactic center, frequent supernova explosions and intense radiation from the active nucleus might sterilize planets, while too far out in the galactic halo, the low abundance of heavy elements might prevent the formation of rocky planets. Our solar system occupies a comfortable position in the galactic disk, far enough from the center to avoid its hazards, but close enough that the gas from which we formed contained sufficient heavy elements to build rocky planets. Galaxies evolve over billions of years, their star formation rates, morphologies, and colors changing as they age. Observations of distant galaxies show us systems as they appeared billions of years ago, allowing astronomers to piece together the history of galactic evolution. Young galaxies in the early universe appear smaller, bluer, and more irregular than mature galaxies in the present day, suggesting that galaxies grow and settle into their final forms over cosmic time through mergers and the gradual consumption of their gas supplies. The Triangulum Galaxy, also known as Messier 33, stands as the third largest member of the local group after Andromeda and the Milky Way. This face-on spiral galaxy lies about 3 million light-years from Earth and contains roughly 40 billion stars, making it much smaller than its two larger companions. The Triangulum Galaxy may be gravitationally bound to Andromeda, possibly orbiting it in a wide elliptical path, and it will likely play a role in the eventual merger between Andromeda and the Milky Way billions of years from now. Ultra-diffuse galaxies represent a mysterious class of objects discovered in recent years, with sizes comparable to the Milky Way, but containing only about 1% as many stars. These ghostly galaxies have such low surface brightness that they're incredibly difficult to detect, and their discovery suggests that many more galaxies might be hiding in the universe than previously thought. The nature of ultra-diffuse galaxies remains unclear, with theories suggesting they might be failed giant galaxies, puffed-up dwarf galaxies, or the remnants of galaxies that lost most of their stars to tidal stripping. The cosmic distance ladder represents the series of techniques astronomers use to measure distances to galaxies. For nearby galaxies, they can identify individual bright stars called Cepheid variables, whose pulsation periods relate directly to their intrinsic brightness, allowing distance determination. For more distant galaxies, mysterious relationships between galaxy properties, like the Tully-Fisher relation, connecting rotation speed to luminosity. Each method builds upon the previous one, allowing us to measure distances across billions of light years. The large and small Magellanic Clouds, visible from the southern hemisphere, are small, irregular galaxies orbiting the Milky Way at distances of about 160,000 and 200,000 light years, respectively. These satellite galaxies contain billions of stars and appear as bright patches in the night sky, having been noted by observers for thousands of years. The Magellanic Clouds are close enough that astronomers can study individual stars within them, providing valuable insights into stellar evolution and the properties of galaxies different from our own. Galaxy groups represent the most common environment for galaxies in the universe, containing anywhere from a few to several dozen galaxies in a region a few million light years across. These groups evolve over time as their member galaxies interact gravitationally, sometimes merging to form larger galaxies or being tidally stripped of their gas and stars. The local group will eventually evolve into a single large galaxy as the Milky Way and Andromeda merge, with the smaller members being absorbed or becoming satellites of the merger remnant. The interstellar medium within galaxies exists in multiple phases with different temperatures and densities. Cold molecular clouds with temperatures around 10 to 20 degrees above absolute zero serve as the sites of star formation, while warm neutral and ionized gas fills much of the space between clouds. Hot ionized gas at temperatures of millions of degrees occupies large volumes around and above the galactic disk, heated by supernova explosions and stellar winds. This hot gas can be detected through its X-ray emission and may eventually cool and rain back down onto the disk, providing fresh material for future star formation. Tidal tails and bridges of stars and gas often connect interacting galaxies, drawn out by gravitational forces during close encounters. The Mice galaxies, named for their long tails of stars stretching behind them, showcase this phenomenon beautifully, with the tails containing billions of stars pulled from the main bodies of the galaxies during their collision. Over time, these tails may fall back into the merging system or become dispersed into intergalactic space, forming some of the diffuse stellar populations observed in galaxy clusters. The metallicity of stars and galaxies provides clues about their formation history and age. Astronomers use the term metallicity to refer to the abundance of elements heavier than hydrogen and helium, even though many of these elements aren't actually metals in the chemical sense. The first generation of stars formed from primordial gas, containing only hydrogen, helium, and trace amounts of lithium, while subsequent generations incorporated heavier elements created by earlier stars. By measuring metallicities, astronomers can determine when different stellar populations formed and how galaxies enriched themselves with heavy elements over time. Ring galaxies like Hoag's object display, a nearly perfect ring of bright blue stars surrounding a yellow central core, with very little visible matter connecting the two. These unusual structures may form when a smaller galaxy passes through the center of a disk galaxy, creating a density wave that ripples outward and triggers star formation in a ring. The rarity of ring galaxies reminds us that galaxy collisions can create a diverse array of structures, depending on the masses, relative speeds, and angles of the colliding systems. The concept of galactic archaeology involves studying the chemical composition, ages, and motions of stars within the Milky Way to reconstruct our galaxy's formation history. Just as archaeologists piece together human history from artifacts and structures, galactic archaeologists use stars as fossils that preserve information about the conditions when they formed. This work has revealed that the Milky Way has consumed numerous small galaxies over its history, with some of their stars still identifiable as distinct kinematic and chemical populations in our galaxy today. Galaxies can appear dramatically different when observed at different wavelengths of light. A galaxy that looks unremarkable in visible light might blaze brightly in infrared wavelengths if it contains large amounts of warm dust heated by star formation. X-ray observations can reveal hot gas and active galactic nuclei invisible in optical images, while radio observations might show vast lobes of emission extending far beyond the visible galaxy. Studying galaxies across the electromagnetic spectrum provides a more complete picture of their properties and the physical processes occurring within them. The formation of the first galaxies in the universe remains one of the great frontiers in astronomy. Current theories suggest that dark matter began clumping together in the early universe, creating gravitational wells into which normal matter fell. Within these dark matter halos, the first stars formed from pristine gas, and over time, these stars gathered into the first small proto-galaxies. These early systems merged repeatedly to build larger galaxies, with the process accelerating as the universe expanded and cooled, allowing more complex structures to form. Modern telescopes like the James Webb Space Telescope can now observe some of these early galaxies, appearing as they were when the universe was only a few 100 million years old. The rotation curves of spiral galaxies, graphs showing how fast material orbits as a function of distance from the center, provide some of the strongest evidence for dark matter. In the outer regions of galaxies, visible matter becomes increasingly sparse, and based on the distribution of stars and gas, orbital velocities should decrease with distance. Instead, rotation curves remain flat or even rise slightly, indicating the presence of substantial amounts of invisible matter extending far beyond the visible disk. This dark matter halo can contain 10 times more mass than all the visible matter in the galaxy combined. Fossil groups represent an intriguing class of galaxy systems where a massive elliptical galaxy dominates a group environment, surrounded by X-ray emitting hot gas, but with few other bright galaxies present. These systems may represent the end state of galaxy group evolution, where most of the original members have merged together to form the central giant elliptical galaxy. The hot gas serves as a record of the group's past, its properties reflecting the combined mass of all the merged galaxies. Barred spiral galaxies contain a distinctive linear structure of stars crossing through their central bulge, with spiral arms emerging from the ends of this ball. About 2/3 of spiral galaxies, including our own Milky Way, possess such bars, which play an important role in funneling gas toward the galactic center where it can fuel star formation and feed the central black hole. These bars aren't permanent features, but can form and dissolve over hundreds of millions of years as gravitational instabilities grow and decay within the rotating disk of stars. The cosmic web, the largest scale structure in the universe, consists of filaments and sheets of galaxies surrounding vast empty voids. Galaxies flow along these filaments toward the nodes where galaxy clusters form, like water flowing through a three-dimensional spider web. This structure emerged from tiny density fluctuations in the early universe, amplified over billions of years by gravity. Simulations of cosmic structure formation, which follow the evolution of billions of particles representing dark matter and gas, reproduce this web-like pattern remarkably well, confirming our understanding of how structure grows in an expanding universe. Green pea galaxies, named for their small round appearance and unusual green color in images, represent a rare class of compact galaxies undergoing intense star formation. The green color comes from highly ionized oxygen in their gas, excited by the intense ultraviolet radiation from massive young stars. These galaxies may provide insights into how star formation stellar halo surrounding the Milky Way extends far beyond the visible disk. A roughly spherical distribution of old stars and globular clusters, reaching out hundreds of thousands of light years from the galactic center. This halo contains only about 1% of the galaxy's stellar mass, but preserves important clues about the Milky Way's early history. Many halo stars move on highly eccentric orbits, quite different from the orderly circular motions of disk stars. And their chemical compositions suggest they formed in small dwarf galaxies later absorbed by the Milky Way. Lenticular galaxies occupy a transition zone between spiral and elliptical galaxies, possessing a disk like spirals but lacking prominent spiral arms and containing little gas or active star formation like ellipticals. These galaxies may represent spirals that have exhausted or lost their gas supplies, or they might form through different evolutionary paths. Their smooth appearance and red colors indicate that most of their stars formed long ago, with little ongoing star formation to produce new generations of blue stars. The peculiar velocities of galaxies, their motions relative to the overall expansion of the universe, reveal the gravitational influence of nearby massive structures. Galaxies don't simply move apart due to cosmic expansion, but also feel gravitational pulls toward concentrations of matter like the Virgo cluster. Our local group falls toward Virgo at several hundred kilometers per second, while the entire structure, including Virgo, flows toward an even larger concentration called the Great Attractor, demonstrating that galaxies respond to gravity on scales of hundreds of millions of light years. Safer galaxies represent a common type of active galaxy, appearing as otherwise normal spirals with exceptionally bright compact cores. These cores emit strongly across the electromagnetic spectrum, powered by matter accreting onto their central supermassive black holes. Safer galaxies come in two main types, distinguished by the width of the emission lines in their spectrum, with the differences possibly reflecting different viewing angles to a dusty torus surrounding the black hole, rather than fundamental differences in the galaxies themselves. The intracluster light in galaxy clusters, a diffuse glow of stars spread throughout the cluster, rather than confined to individual galaxies, contains a significant fraction of the cluster's total stellar mass. These stars were stripped from galaxies during close encounters and now orbit in the gravitational potential of the cluster as a whole. Studying this diffuse light helps astronomers understand the violent histories of galaxy clusters and the processes that remove stars from galaxies as they interact. Polar ring galaxies display a ring of stars, gas, and dust orbiting perpendicular to the main disk of the galaxy, creating a striking appearance like a planet with rings oriented in an unusual direction. These systems likely form when a galaxy captures material from a passing companion, with the captured matter settling into an orbit at a large angle to the original disk. The existence of stable polar rings tells us about the three-dimensional distribution of dark matter in galaxies, as only certain mass distributions can support such structures. The look-back time to distant galaxies means we observe them not as they are today, but as they were when their light began its journey toward us. A galaxy 10 billion light years away appears as it was 10 billion years ago, when the universe was only about a quarter of its current age. This light travel time effect turns telescopes into time machines, allowing astronomers to observe cosmic history directly by studying galaxies at various distances, each one revealing conditions at a different epoch in the universe's evolution. Brightest cluster galaxies, the enormous elliptical galaxies that sit at the centers of galaxy clusters, rank among the largest and most massive galaxies in the universe. These giants can contain trillions of stars and span millions of light years, far exceeding the size and mass of galaxies like the Milky Way. They grow through the continual accretion of smaller galaxies falling into the cluster center, a process called galactic cannibalism that builds ever larger systems over cosmic time. The cosmic microwave background radiation, the afterglow of the Big Bang, shows tiny temperature fluctuations that represent the seeds from which all cosmic structure grew. Regions that were slightly denser than average eventually collapsed under their own gravity to form galaxies and galaxy clusters, while underdense regions became the voids we observe today. By studying the statistical properties of these primordial fluctuations, astronomers can test theories of the universe's earliest moments and constrain the properties of dark matter and dark energy. Galactic winds driven by stellar feedback and active galactic nuclei can expel gas from galaxies at speeds of hundreds or thousands of kilometers per second. These outflows play a crucial role in regulating galaxy growth by removing the raw material for star formation and enriching the intergalactic medium with heavy elements forged in stars. Observations show that outflows are common in actively star-forming galaxies, with the wind strength correlating with the star formation rate, suggesting a self-regulating mechanism where intense star formation triggers winds that suppress further star formation. The zone of avoidance, a region of sky along the plane of the Milky Way, poses challenges for observing distant galaxies because dust in our own galaxy absorbs and scatters their light. This obscuration makes it difficult to create complete maps of the nearby universe, as galaxies hiding behind the Milky Way's disk remain invisible to optical telescopes. Radio and infrared observations can penetrate the dust better than visible light, helping astronomers fill in these gaps in our knowledge of the local cosmic neighborhood. Blue compact dwarf galaxies, small star-forming galaxies with unusual properties, appear to be forming stars so vigorously that they would exhaust their gas supplies in just a few hundred million years. These galaxies may represent systems that have recently acquired fresh gas through mergers or accretion from the cosmic web, triggering an intense but brief period of star formation. Their low masses and metal content suggest they might resemble the building blocks from which larger galaxies assembled in the early universe. The gravitational potential wells of galaxy clusters can trap gas so effectively that it would take billions of years for the gas to cool and fall into the cluster galaxies to form stars. This cooling problem suggests that some mechanism must prevent the gas from cooling, likely heating provided by the central active galactic nucleus, which injects energy through jets and bubbles of relativistic particles. This feedback creates a delicate balance between cooling and heating that maintains the hot gas in a quasi-steady state over cosmic time. Compact elliptical galaxies represent a rare class of small, dense galaxies that may be the stripped cores of larger galaxies. When a galaxy passes too close to a more massive companion, tidal forces can remove its outer stars, leaving behind only the dense central region. These compact ellipticals contain surprisingly old stellar populations, despite their small sizes, supporting the idea that they are remnants of larger systems rather than intrinsically small galaxies. The Tully-Fisher relation connects the rotational velocity of spiral galaxies to their intrinsic luminosity, providing a useful tool for measuring cosmic distances. Galaxies that rotate faster tend to be more luminous, reflecting the fact that more massive galaxies have stronger gravity and thus higher rotation speeds. By measuring a galaxy's rotation curve and applying this relation, astronomers can determine its intrinsic brightness and compare it to the observed brightness to calculate the distance, a technique that works for galaxies too distant for other methods. Galaxy harassment describes the cumulative effect of many high-speed encounters between galaxies and clusters, which gradually transform disk galaxies into spheroidal systems. unlike major mergers that dramatically reshape galaxies in single events. Harassment involves repeated close passes that strip away gas and stars, puff up disks, and eventually leave behind objects resembling dwarf elliptical galaxies. This process may explain why galaxy clusters contain fewer spiral galaxies and more ellipticals than the field population. The ARP Catalog of Peculiar Galaxies, compiled by Halton ARP in the 1960s, showcases galaxies with unusual appearances, often resulting from interactions and mergers. This collection includes systems with tidal tails, distorted disks, multiple nuclei, and other features that deviate from the standard spiral and elliptical morphologies. Many of these peculiar galaxies have become iconic objects for studying galaxy evolution, with names like the Antennae galaxies and the Tadpole galaxy reflecting their distinctive shapes. Low-surface brightness galaxies have so few stars per unit area that they're difficult to detect against the night sky background, despite containing significant total masses. These diffuse galaxies might be quite common, but have been historically underrepresented in surveys because traditional techniques favor the detection of brighter, more compact systems. The discovery of large numbers of low-surface brightness galaxies has revised upward estimates of the total number of galaxies in the universe and raised questions about how such diffuse systems form and survive. The fundamental plane of elliptical galaxies describes a tight correlation between their size, surface brightness, and velocity dispersion, providing insights into the physical processes that shape these systems. This relationship suggests that elliptical galaxies form a relatively homogeneous class, despite their range of sizes and masses, possibly reflecting a common formation mechanism through mergers of disk galaxies. Deviations from the fundamental plane can indicate unusual formation histories or recent merger activity. Galactic fountains describe the circulation of gas between the disk and halo of spiral galaxies, driven by supernova explosions that heat gas and launch it to high altitudes. This hot gas rises above the disk, cools as it expands, and eventually falls back down, completing a cycle that can take tens of millions of years. The fountain process helps mix heavy elements created in the disk throughout the galaxy and may trigger star formation, where falling gas clouds collide with the disk. The Hubble sequence, often depicted as a tuning fork diagram, classifies galaxies by their visual appearance into ellipticals, lenticulars, and spirals, with spirals subdivided by how tightly wound their arms appear. While useful for organizing galaxy types, this sequence doesn't represent an evolutionary progression as once thought. Galaxies don't evolve from one type to another along the sequence in a simple way, though major mergers can transform spirals into ellipticals, and gas depletion can turn spirals into lenticulars. Interacting galaxy pairs like the Antennae galaxies showcase star formation, triggered by gravitational perturbations during collisions. The interaction compresses gas clouds, causing them to collapse and form new stars at rates much higher than in isolated galaxies. These collisional starbursts produce spectacular fireworks displays of massive young stars, though the burst will eventually exhaust the available gas, leaving behind a merged system with little ongoing star formation. The redshift of galaxies, the stretching of their light toward longer wavelengths as the universe expands, provides both distance information and a way to measure the expansion rate. Nearby galaxies show small redshifts corresponding to modest recession velocities, while distant galaxies can have redshifts greater than 1, meaning their light has been stretched to more than twice its original wavelength. The relationship between redshift and distance, encoded in Hubble's law, reveals that the universe is expanding uniformly, with every region of space stretching at the same rate. cataclysmic variables in galaxies, binary star systems where one member transfers mass to a white dwarf companion, can produce nova explosion when enough material accumulates on the white dwarf's surface. These novae, while far less energetic than supernovae, still brighten dramatically and can be detected in nearby galaxies, helping astronomers study stellar populations and the late stages of stellar evolution in different galactic environments. The missing satellite problem notes that simulations of galaxy formation predict far more small satellite galaxies around large galaxies like the Milky Way than observers actually detect. This discrepancy might reflect the difficulty of forming stars in very small dark matter halos, or it could indicate problems with our understanding of dark matter or galaxy formation. Recent discoveries of ultra-faint dwarf galaxies around the Milky Way have partially alleviated the problem, but haven't completely resolved it. Galaxies in the early universe appear to have formed stars more efficiently than modern galaxies, converting larger fractions of their gas into stars over shorter timescales. This cosmic downsizing, where the most active star formation shifted from massive galaxies at high redshift to smaller galaxies at later times, reflects changing conditions in the universe as it expanded and cooled. Gas became harder to compress into star-forming clouds over time, and feedback from stars and active galactic nuclei became more effective at regulating star formation. The stellar mass-halo-mass relation connects the mass of stars in a galaxy to the total mass of its dark matter halo, revealing an efficiency curve that peaks at intermediate masses. Both very low mass and very high mass halos contain fewer stars than expected from their total mass, suggesting that feedback processes prevent these systems from converting their gas into stars as efficiently as intermediate mass halos. Understanding this relation helps constrain models of galaxy formation and the various physical processes that regulate star formation. Dwarf irregular galaxies like the Small Magellanic Cloud contain significant amounts of gas relative to their stellar mass and show active star formation despite their small sizes. These galaxies lack the organized structure of larger spirals, but often contain regions of recent star formation, visible as bright knots of blue stars and pink nebulae. Their low masses mean that supernovae and stellar winds can more easily drive gas out of these systems, potentially explaining why they haven't converted all their gas into stars. The cosmic star formation history, derived from observations of galaxies at different redshifts, shows that the universe's overall star formation rate peaked about 10 billion years ago and has been declining ever since. This decline reflects the exhaustion of gas supplies in galaxies and increasingly effective feedback that prevents remaining gas from forming stars. The universe today forms new stars at a rate roughly 10 times lower than at the peak of cosmic star formation, suggesting we live in a slowly fading cosmos where the era of vigorous star formation has largely passed. Mergers between galaxies of similar masses, called major mergers, can completely restructure both systems, destroying disks and forming elliptical galaxies from the merger remnant. These violent events scramble stellar orbits, trigger intense starbursts, and can activate quasars by funneling gas into the central black holes. Simulations of major mergers reproduce many features seen in observed peculiar galaxies, confirming that mergers play important roles in galaxy evolution, despite being relatively rare events in the present-day universe. The Faber-Jackson relation for elliptical galaxies connects their luminosity to the velocity dispersion of their stars, providing a distance indicator similar to the Tully-Fisher relation for spirals. More luminous ellipticals have stars moving faster on average, reflecting their stronger gravitational fields. This relation, along with the fundamental plane, helps astronomers understand the properties of elliptical galaxies and measure distances to galaxy clusters. Shell galaxies display concentric shells or ripples of stars in their outer regions, likely created when a small galaxy merges with a larger elliptical. As the smaller galaxy dissolves, its stars continue to oscillate in and out through the center of the elliptical, creating the observed shells at the turning points of their orbits. These shells fade over time as the orbits randomize, but they can remain visible for billions of years, serving as fossil evidence of past merger events. The initial mass function describes the distribution of stellar masses in a population of newly formed stars, with low-mass stars vastly outnumbering high-mass stars. This function appears to be remarkably universal across different galaxies and environments, suggesting that the same physical processes govern star formation wherever and whenever it occurs. Understanding why the initial mass function takes this particular form remains an important goal in astrophysics. Galactic bulges, the central concentrations of stars in spiral galaxies, come in two main types with different properties and formation histories. Classical bulges resemble small elliptical galaxies embedded in the disk, containing old stars and showing no rotation, likely formed through mergers early in the galaxy's history. Pseudobulges rotate significantly, contain younger stellar populations, and form through secular evolution processes like bar-driven gas inflow that builds up the central density over time. The void galaxies living in the vast empty regions between filaments of the cosmic web tend to be smaller, bluer, and more gas-rich than galaxies in dense environments. These systems have experienced fewer interactions and mergers than their counterparts in groups and clusters, preserving more of their gas and continuing to form stars at modest rates. Studying void galaxies helps astronomers understand how environment affects galaxy evolution by providing examples of systems that have evolved in relative isolation. Luminous infrared galaxies emit most of their energy at infrared wavelengths, often producing hundreds of times more infrared light than the Milky Way. This infrared emission comes from dust heated by intense star formation or active galactic nuclei, with the dust absorbing ultraviolet and optical light and radiating it in the infrared. Many luminous infrared galaxies turn out to be merging systems where the collision has triggered powerful starbursts, making them important laboratories for studying star formation in extreme conditions. The Butcher-Roemmler effect describes the observation that galaxy clusters at high redshift contain larger fractions of blue, star-forming galaxies than nearby clusters. This evolution reflects the gradual transformation of cluster galaxies over cosmic time. As star-forming spirals exhaust their gas, or have it stripped away through interactions with the hot intracluster medium, eventually becoming passive red galaxies. The effect demonstrates that galaxy clusters are not static systems, but evolve significantly over billions of years. Galactic corona, the extended halos of hot gas surrounding galaxies, contain substantial reservoirs of baryonic matter that may rival or exceed the mass of stars and cold gas in the galaxy. This hot gas, at temperatures of millions of degrees, emits X-rays and represents a reservoir from which galaxies can draw to fuel future star formation as it cools and accretes onto the disk. Understanding the properties and evolution of galactic coronae helps explain how galaxies maintain their gas supplies over cosmic time. The morphology density relation shows that elliptical and lenticular galaxies are more common in dense environments like galaxy clusters, while spiral galaxies dominate in lower density regions. This relationship reflects environmental processes that transform spirals into spheroidals in crowded regions through mechanisms like ram pressure stripping, galaxy harassment, and tidal interactions. The relation demonstrates that galaxy evolution is influenced not just by internal processes, but also by the surrounding environment. Superbubbles in galaxies, giant shells of hot gas hundreds of light years across, form when multiple supernovae explode in proximity, with their combined energy creating enormous cavities in the interstellar medium. These structures can blow holes in the galactic disk, allowing hot gas to escape into the halo and potentially driving galactic winds. Superbubbles play important roles in shaping the structure of the interstellar medium and regulating star formation in actively star-forming galaxies. The color magnitude diagram for galaxies reveals a bimodal distribution with a red sequence of passive galaxies that have ceased star formation and a blue cloud of actively star-forming systems. The relative numbers of galaxies in these two populations change with cosmic time, with the red sequence growing more populated as the universe ages and galaxies exhaust their gas supplies or have their star formation quenched by environmental or internal processes. A green valley between the two populations may represent galaxies in transition from star-forming to passive. Ram pressure stripping occurs when galaxies move through the hot gas, filling galaxy clusters. With the pressure of this tenuous medium pushing against the galaxy's own gas and stripping it away like wind removing leaves from a tree. This process can completely remove a galaxy's cold gas reservoir over hundreds of millions of years, transforming a star-forming spiral into a passive lenticular galaxy. Galaxies stripped of their gas often show asymmetric distributions of remaining gas and one-sided tails of stripped material trailing behind them as they orbit through the cluster. Post-starburst galaxies, also called E+ galaxies, show spectral signatures indicating they recently ceased forming stars after a period of intense star formation. These systems contain substantial populations of a type stars, which are relatively short-lived, but little ongoing star formation or gas content. They may represent galaxies caught in the act of transitioning from the blue cloud to the red sequence, perhaps following a merger that consumed all available gas in a final burst of star formation. The stellar initial mass function may vary slightly in different environments, with some evidence suggesting that starbursts in merging galaxies produce a top-heavy initial mass function weighted toward massive stars. If true, this variation would affect how we interpret observations of distant galaxies and could help explain some puzzling observations of galaxy properties at high redshift. However, the universality of the initial mass function remains an active area of research and debate. Galactic thick disks, found in many spiral galaxies including the Milky Way, consist of older, more metal-poor stars orbiting with larger vertical motions than thin disk stars. These thick disks may form through various mechanisms, including early intense star formation, accretion of satellite galaxies, or dynamical heating of the thin disk by mergers and perturbations. The thick disk preserves information about conditions in the galaxy several billion years ago when these stars formed.